Hello everyone, sorry I'm not here today, uh, but we're going to be kicking off this new unit by looking at Hooke's law, which has to do with how springs work. So as you can see on the board there, Hooke's law says F, might be hard to see, the subscript on the F is S for spring force. The magnitude of the spring force is equal to K, which is known as the spring constant, times delta X. So what delta X is the displacement of the spring from its equilibrium position. So if you have a spring, like this one right here, this is its equilibrium position. When it is sitting at rest, nothing is stretching or compressing the spring. If I then stretch the spring, you know it tends to kind of exert a force to snap back. If I let go, it snaps back. And the force that it is exerting on the end is proportional to how much it has stretched by. That's what that delta X is, the displacement of the spring. So if I measure the length of the spring right here, and then stretch it, measure the length of the spring right here, subtracting those two gets me the displacement. So we're going to do a little activity to see how that works. So there are several springs. You'll pick one out, and they all have little piece of blue tape that has a label. This one is number 2. They all have numbers on them, and on your sheet there are the theoretical spring constants for each one. So obviously you'll only use one of those because you only have one spring. So this activity, we're going to be looking at spring force. So the first thing we need to do is measure the unstretched length of our spring. So that's your first step. Take a tape measure. Measure how long the spring is when it's not stretched. And then we're going to be using a force sensor to collect data on the spring. You guys know how NuLog works. You have to plug the sensor into the USB bridge, plug them together, and then you plug the USB to your computer, open the NuLog application, and all that. Don't forget, if it doesn't work, try restarting the program, try restarting your computer, all that fun stuff. The force sensor we've used before. Remember there's this hook here, or maybe we haven't used before. I don't remember. I think we did. Regardless, there's this hook here, and if you pull on the hook, apply a force, the sensor will measure how much force is being exerted on the hook, or how much force the hook is exerting, which are the same thing by Newton's third law. So we're going to use this force sensor to see how much force our spring exerts. We're using a ring stand to make this easier, and you're going to set up your ring stand and just loop the spring over it. The springs all have this little loop thing on the end, so you can just slide it over the ring stand, and you've got one end of your spring anchored. Right? Then the other end of your spring you can hook on the force sensor. You should zero your force sensor. There's a reset button on NuLog. You should reset your force sensor with it not doing anything. But then, hook your spring and stretch it some length. And then you're going to record. And you notice if I do this, the ring stand moves. So somebody will need to hold the ring stand in place. But then you're going to record the force that the sensor is exerting. And you're going to do that for 10 different lengths. So set it somewhere here, record the force, and go a bit bigger, record the force, etc. Maybe the first thing you should do is stretch out your spring to see how far it can stretch without distorting. Then you'll know that's the highest value, and then you can split up how much you want to move it each time to get 10 values for force. And at each place, you'll also be measuring the displacement of the spring. This is where it comes in handy to have group members, because you really don't have enough hands to do this on your own, but have somebody just holding the tape measure and measuring how long the spring is at each point. So then you'll have data on the length of the spring versus force to put into the table on your sheet. And then as I said, to find the displacement, you just take this length, how long the spring was, and subtract off the equilibrium length of the spring that you found up there. Once you have all that data, you're going to make a scatter plot, put displacement on the x-axis, force on the y-axis, label your axes, label your scale, make a scatter plot of the data. Then you're going to draw a best fit line, find an equation for the best fit line. Here, the best fit line that you draw. Go to your calculator, do a linear regression on the data. Input your displacement values into L1, your force values into L2, and then go stat calc linreg. If you forget how to do that, I'm sure somebody in the class knows, and you can ask them, because we've done it before in this class. And record the result below. If you have to turn diagnostics on, and then you'll also get an R value, which is the correlation coefficient, which tells you how close your data is to being linear. And then from those results, you'll get a value for the spring constant, and then you'll see how linear your results are, and then compare the spring constant you get to the theoretical spring constants listed on the first page. This is the theoretical spring constant for your spring, and then you'll write a conclusion. Yeah, that's it. That's what you'll be doing in your normal table groups, and then you'll just turn in this packet thing next class as a part of your homework. So there isn't a full lab write-up for this. That's it. If you have any questions, if you find you have any questions afterward, you can come see me on Wednesday. Have fun!